Chinese remainder theorem. The linear system of congruences X congruent to AI mod Mi, where the moduli are pairwise relatively prime and 1 less than or equal to I less than or equal to K, has a unique solution modulo the product M1, M2, M3, etc. Mk. That is, consider the system of linear congruence as X is congruent to A1 mod M1, X is congruent to A2 mod M2, etc. X is congruent to AK mod Mk. Then and one condition is there, this moduli M1, M2, etc. Mk are pairwise relatively prime. Then this system of linear congruence has a unique solution modulo the product M1, M2, M3, etc. Mk. This is the statement of Chinese remainder theorem. That means this system has a unique solution one if these moduli are pairwise relatively prime. Okay, this is the statement. Now we want to write the proof of this theorem. For proving, we take capital M is the product of small m1, small m2, etc., small mk, and we take a new term as capital Mi. Capital Mi is product of the above congruence of capital M divided by small mi. For I is 1 less than or equal to I less than or equal to K. That means capital Mi, that is capital Mi is equal to small m1, small m2, etc. small mi minus 1, small mi plus 1, etc. small mk whole divided by mi. That means we can cancel these two mi. So remaining this m1, m2, etc. mi minus 1, mi plus 1, etc. mk. Now given small m1, small m2, etc. small mk are pairwise relatively prime, which implies, that means what is the pairwise meaning of relatively prime? Pairwise means GCD of m1, m2 1, GCD of m1, m3 is equal to 1, etc. GCD of m1, mk minus mk is equal to 1. Now GCD of m2, m3 is equal to 1. Taking any two moduli, if we take any pair of moduli, that GCD is always 1. So that means the moduli are pairwise relatively prime, which implies GCD of capital Mi comma small mi. That means in this product small mi is not here and all others are pairwise relatively prime. So mi is not a factor of this product. So GCD of capital Mi and small mi is equal to 1. Also, this capital Mi is equal to product of m1 into m2 into etc. That means this is capital Mi is a product of m1 when I not equal to 1. Capital Mi is a multiple of m1 when I not equal to 1. Capital Mi is equal to multiple of m2. Similarly, we can write small m2 when I not equal to 2, etc. In general, capital Mi is a multiple of mj when I not equal to j. So we can write this as this in terms of congruence as Mi, capital Mi is congruent to 0 mod mj when for I not equal to j, Mi is congruent to 0 mod this. This is taken as equation 1. This is taken as equation 2. Here, the proof, we want to prove this Chinese remainder theorem. There are two steps. First is to find a solution and then prove this solution is unique. That is two conditions. One is find a solution and other is to prove the uniqueness. First, to construct a solution. To construct a solution. First step is to construct the solution. How to construct the solution? For this, we take x is equal to. For this, before that, we have GCD of capital Mi, small mi is equal to 1. GCD of capital Mi, small mi is equal to 1 using equation 1. We already have a theorem that the linear congruence Ax congruent to B mod n has a unique solution if and only if GCD of A and n is equal to 1. The linear congruent, we already discussed the theorem. Ax congruent to B mod m has a unique solution if and only if GCD of A and n is equal to 1. Here, GCD of Mi, small mi is equal to 1. Then using this theorem, we can write the congruence. Therefore, the linear congruence Mi x is congruent to 1 mod Mi has a Mi x is congruent to 1 mod Mi x Mi y congruent to 1 mod Mi has a unique solution. We take that solution as yi. Say yi be the solution. Therefore, the congruence Mi yi is congruent to 1 mod Mi. Capital Mi yi congruent to 1 mod small mi. This is another form. We can say that this yi is the inverse of capital Mi mod small mi, or vice versa. We already discussed this topic last chapter. Now let x is equal to a1 capital M1 y1 plus a2 capital M2 y2 plus etc. plus ak capital MK yk. Next, to show that this next we show that this X is a solution of the given system. This X is a solution of the given system. For that, we write this X as sigma I is equal to 1 to k ai mi capital Mi yi, and take jth term. Here I varies from 1 to k, and we take the jth term separately from this equation. We can write x is equal to sigma I from 1 to k ai capital Mi yi. Here I not equal to j. Jth term ഇവിടെ എടുക്കുന്നില്ല, സെപ്പറേറ്റ് ചെയ്യുന്നു. jth term separate plus aj mj yj. We take jth term separately. So take it equation 1, equation 3. Now we have this equation. Second equation, capital Mi is congruent to first equation is capital Mi is congruent to 0 mod mj, small mj. From this, multiply both sides by ai and yi is congruent to 0 into ai yi is 0 mod mj. So ai mi yi is from this equation, mi is congruent to 0 mod mj implies ai mi yi is congruent to 0 mod small mj. This is the property of linear congruence. A congruence to b mod m implies ac congruent to bc mod m. So here we multiply ai yi on both sides of this equation, we get this line. Here I not equal to j, here I not equal to j. So sigma I is equal to adding these congruences except j, ai mi yi is congruent to 0 plus 0 plus 0 plus etc. That means 0 mod mj. So from this equation 3, first term is 0, taking mod mj. Now mj yj, what is the second term? How to convert this second term? Here by previous section, this mi yi is congruent to 1 mod mi. Mi yi is congruent to 1 mod mi. We have GCD of capital MJ comma small mj is equal to 1, which implies from this equation mi yi is congruent to 1 mod mi implies mj yj is congruent to 1 mod small mj. So substituting this 0 and this 1 in the previous equation 3, when it is taking modulus small mj, then equation 3 becomes 3 becomes x congruent to x, taking mod mj, x congruent to this summation becomes 0, 0 plus, and this aj mj yj, aj from this term aj mj yj, this mj yj is congruent to 1 mod small mj. So aj into 1, so plus aj into 1, this one, aj into 1 mod small mj. So x is congruent to aj mod mj. So that is this x. What is x? X is this value, this sum x. This summation x satisfies the jth equation. Here jth equation is arbitrary, so therefore x congruent to aj mod mj for all j, for all 1 less than or equal to j less than or equal to k. That means this x is equal to a1 m1 y1 plus a2 m2 y2 plus etc plus ak mk yk. This x satisfies all equations of this system of linear congruences, which implies this x is a solution of the given linear congruences. That is, thus x satisfies every congruence in the system. So x is a solution of the given linear system. Next, to prove the uniqueness. How to prove the uniqueness? For uniqueness, we take two solutions. There are two solutions. Let x0 and x1 are two solutions of the given system. Therefore, these values x0 and x1 satisfies every equations of the given system. That means x0 is congruent to aj mod mj, and x1 is also another solution. So x1 is congruent to aj mod mj for every j. എല്ലാ ഇക്വേഷനും സാറ്റിസ്ഫൈ ചെയ്യുന്നുണ്ടല്ലോ. For 1 less than or equal to j less than or equal to k. Here again applying the properties of congruence. This is x0 congruent to aj mod mj, x1 congruent to aj mod mj. Consider this as two linear congruences, then x0 minus x1 is congruent to aj minus aj mod mj by the properties of congruence. Therefore, we have x0 minus x1 is congruent to aj minus aj mod mj. So x0 minus x1 congruent to 0 mod mj for every j, for all j. That means mj divides x0 minus x1 for all j. That means m1 divides x0 minus x1, comma m2 divides x0 minus x1, etc. mk divides x0 minus x1. We already have m1 divides a term, m2 divides another term, etc. mk divides a term, then the LCM of m1, m2, etc. mk divides this x0 minus x1. Thus, the LCM of m1, m2, etc. mk divides x0 minus x1. Here m1, m2, etc. mk are pairwise relatively prime. Then the LCM of these k numbers is the product m1, m2, etc. mk divides x0 minus x1. Since mi's are pairwise relatively prime, pair mj's are pairwise relatively prime, pairwise relatively prime, pairwise relatively prime. So this product is we taken as capital M. This is taken as capital M. So capital M divides x1 minus x0. So x1 minus x0 is a multiple of capital M. So x1 minus x0 is congruent to 0 mod capital M. So x1 is congruent to x0 mod capital M. x0 mod capital M. So x1 congruent to x0 mod capital M, that is x1 congruent to x0 mod capital M is small m1 into small m2 into etc. small mk. Therefore x1 and x2 are same, x1 and x0 are same. Therefore any two solutions, x1 and x2 are two solutions. Therefore any two solutions of the linear system are congruent modulo m. Congruent modulo capital M. So the solution is unique. So the solution is unique. So the solution is unique modulo capital M. Capital M is the product small m1, small m2, etc. small mk. Just a proof.